The effects of 4 types of graphite coder on light box readings are to be studied. Since readings will differ from day to day, observations are taken on each of the 4 types every day. The results are as follows. So we have the graphite coder types, and we have the days. So they're using days here as blocks. I'll explain why that's true in a moment. They have here a summary set of data. They tell us the sum of squares for total, and they tell us the sum of all the observation values, where all these values total up to be when you add them. And then it tells us create the ANOVA table for this data, and at the 5% significance level, test the claim that all the graphite coders produce the same average light box readings. So when I read the problem, I indicated earlier that I thought it was the randomized block design layout. And the reason why is that, first of all, I can see that every value in the table, every number, can be classified in 2 ways. In other words, this 5 isn't just part of graphite coder K, right? It's also part of day 1. So we can see that it has 2 ways to classify it. It's got K as part of it, and day 1 is another part. You don't see that in a completely randomized design. And as far as the other part of it is that, it's not that there isn't another type of experimental design that has this dual classification system. It's that here, they kind of implied here that the readings will differ from day to day. And they know this. It says, since readings will differ from day to day. So it seems like they don't really care about this effect, right? They're aware that it changes day to day. They're not concerned with it. They really just want us to figure out which coders, right? Test the claim that all of the graphite coders produce the same average light box readings. So what they want to do essentially here is to say, let's figure out, which coder works the best. But we're aware that we don't want to confound graphite coders with the days. Confounding means we don't want the differences in the days to obscure the differences between the graphite coders. So we block them out by putting them separate like that, and that way we can compare them, along the same day we'll compare all the coders. So along the same day we'll compare all the coders, and along the same day we compare all the coder types, right? So as we block out the days, the differences that are going to be produced by the different days will be blocked out in the procedure. So again, I think randomized block design is most appropriate here. So we're going to go ahead and use that approach. Another thing about randomized block design before we begin is that we assume there's no interaction effect. What that means essentially is that, the days and the graphite coder types aren't going to affect one another in a strange way. In other words, if M is the best graphite coder or the worst graphite coder, let's say, it'll be the worst across all the days. And if K is the best, it'd be the best across all the days. So that's the pattern that we would expect. If there's an interaction effect, it might be something like, whatever makes day 3 different from day 1 might also mysteriously make K the worst level that day, but on every other day it's the best. So if that sort of thing exists, that would be called an interaction effect. So there's some reason why K and day 3 combine to produce an unexpected result. Our belief in randomized block design is that those interaction effects do not exist. So that, again, as I said before, if it turns out K is the best graphite coder type, it'll be the best across all 3 days. Okay, so that's the idea. Let's go ahead and work out the problem now using the steps to do a randomized block design. The first thing we have to do is come up with a claim, of course. So the claim in our case is going to be basically saying that right here what this says, test the claim that all of the graphite coders produce the same average light box readings. So let's begin with that statement first. So we're going to test the claim that the mean for M is equal to the mean level for A is equal to the mean for K is equal to the mean for L. Okay, so we're just saying that all the means for the 4 treatments are the same. And of course now for HO and HA, we will then express the corresponding hypotheses that stem from that. Here you see that this claim is the same as our typical HO, so I'll just repeat that down here for HO. The idea that all of them are the same. And HA, of course, is that at least one differs significantly from the rest, right? At least one differs significantly from the rest, from the others, right? Okay, so at least one differs significantly from the others. All right, so that's our HA, our HO, and we have our claim in there expressed. All right, the next step of the problem then is going to be to work with the data. And the data step can be complicated, so remember we're going to have to basically work that out on a different sheet of paper, and we'll come back and fill in our results in the table. So I'm going to write here data, but what I really want to do is fill out the ANOVA table. So what I want to do is to draw the ANOVA table here, then we'll go get the numbers to fill it in. Okay, so to draw the ANOVA table, I'm just putting a box, and I'm going to express here source, like we've done in the past. This is the source of the variation, then degrees of freedom. Then we'll need the sum of squares. We'll need the mean sum of squares. And then finally from there, we'll end up with an F-test statistic. Okay, now for the sources, in a randomized block design, we have variation coming from the treatments. We have variation coming from the blocks, from the random error, and then of course we have a total row here at the bottom. Okay, so there is our results here. So we're going to fill in this information when we come back, and at that point, we can carry on the rest of the hypothesis test when we're done. Okay, the first thing we do in our data step is to calculate the correction factor, the CF, and that's basically calculated by doing the summation of the response variable y, quantity squared, over n, the number of values. So they gave us this quantity, the summation of yi, so we have that, it's 57.4, and we're going to square that value and then divide by the number of values we had. Well, we had 4 columns of 3, so we're going to call that 12 total values, of course, right? All right, so let's see what that works out to be as an answer. We have 57.4 squared divided by 12. And when we do that, we get 274.563 repeating. 274.563 repeating. And I'm going to go ahead and store that answer in my calculator as a variable x, so we have it for later. Okay, now, next thing we calculate normally is the total sum of squares. But that's given to us here. It's 2.276 repeating. That's basically all we need from that, so I'm going to go ahead and cover that up to give us more space there. Okay, now, from there, let's go ahead and work on the next part, which is the sum of square for treatments, SST. So it's the same thing we calculated in the completely randomized design experiment, just now we're dealing with the same quantity, but in the randomized block design. So, first thing you want to do is put the treatment total for graphite coder M squared over the number of values in that column, which is 3. If you notice, that's also the same as the number of blocks, which it has to be under this design. So that means that you can just put B here as a notation to tell you that the number of values is equal to the number of blocks. Okay, and then we'll do that all the same all the way across, right? So T for A squared over B plus dot, dot, dot. The last one, T of L squared over B, right? Minus the correction factor. So if we work that out for us, we're going to have this treatment total is 12.8. 12.8 squared over 3 plus, here we'll have 9 is 13, and then 14.6, right? 14.6 squared over 3. And then we'll do the next one, it's going to be 15.8 over 3 plus 15.8 squared over 3 plus, that's 9.6, so 14.2 squared over 3 minus our correction factor. So minus the correction factor in the problem. All right, let's work that out on our calculator and see what we get for that calculation then. So 12.8 squared divided by 3 plus 14.6 squared divided by 3 plus 15.8 squared divided by 3 plus 14.2 squared divided by 3. All that minus the correction factor x. And when we're done, we end up with the answer 1.53. So the sum of square for treatment is 1.53. Okay, so remember that's your sum of square for treatment. All right, next step in the process is to calculate something called the sum of squares for blocks. The sum of squares for blocks. So the sum of squares for blocks is just like the sum of squares for treatment, except for we're dealing with the blocks in this case. So in other words, we want to have the block totals squared over the number of values in the blocks. So block 1 squared over the number of values. Now you'll notice there are 4 values because that's how many treatments we have. We have k treatments, which is 4 in this case. So we just put k at the bottom, just like we put v down here. Then we'll have block total 2 squared over k plus block total 3 squared over k. And then minus the correction factor, of course. Now the block total going across, this first block total is 18.4. We'll square that and divide by the number of values we have, which is 4, plus the next block total, which is 19.6 squared over 4, and then the last block total, which is 19.4 squared over 4, and then minus the correction factor. Okay, so let's see what that works out to be. So we're going to have 18.4 squared divided by 4 plus 19.6 squared divided by 4 plus 19.4 squared divided by 4 minus the correction factor, which I stored in my calculator as x a while ago. We'll get the answer 0.206 repeating. 0.206 repeating. Okay, so there we have that. Now, after that, the thing we usually calculated last, and we'll still calculate last here before we move back to our table and fill in the ANOVA table, is the sum of square for error. The sum of squares for error. Now, if you remember, the sum of square for error we said was difficult to calculate, so we did it using a backdoor approach. The idea behind it was that if we took the total sum of squares, this is what we said before. We said if we took the total sum of squares and we subtracted off the sum of square for treatment, we'd end up with SSE. Well, now we're going to subtract off not just the sum of squares for treatment, but also the sum of squares for blocks. And by doing that, we'll be left over with the error. So basically what we're doing is we're taking the total variation in the sample and we're saying it's attributable to 3 sources: to the treatment, to the block effect, the treatment effect, and the random error that's occurring naturally. So that's where all the variation we find in our sample data comes from. It comes from the treatment effect, the blocks effect on the data, and then the random error, which we haven't accounted for in either of these 2 variables. And when you're done, you end up with, a total sum of squares. So if we take the total sum of squares, subtract off the treatment effect, subtract off the block effect, we'll be left with only what's left over, which is the random error. So that's kind of the idea. All right, not kind of, it's exactly the idea. So we're going to take the total and subtract off these numbers. So it's 2.276 repeating minus 1.53 minus 0.206 repeating. Let's see what that ends up giving us for the sum of square for error. Okay, so we'll have 2.2766666 repeating minus 1.53 minus 0.206 repeating, right? And when you're done with that, you end up with the answer 0.540 essentially. 0.540. So 0.540. All right, so 0.540 is your SSE. Let's take those values now and put them into our ANOVA table. So what we want to do is pull back the paper we had before and then fill in what we had listed there for the ANOVA table. Okay, so let's go ahead and do that then. We're looking at the treatments here. What are the degrees of freedom for treatments? Well, in order to answer that, we have to simply say, well, how many treatments did we have and take away 1? Well, you notice we had 1, 2, 3, 4 treatments. If we take away 1, we end up with 3, right? All right, what about the degrees of freedom for blocks? Well, we had, remember, 3 different blocks, right? The number of blocks was 3, so we take away 1, we end up with 2. The total sum of squares is basically, the total degrees of freedom, is basically the number of values we had. We had 12 values minus 1, so that will give us 11. Now, if you look at this, we have 5 accounted for here. We have to have something that will add up to 11 now put here in this block. It's got to be 6, right? Or 11, take away 2, take away 3 is equal to 6. So 11 minus 5 is 6, so that's where we put 6 into the error. So we get the degrees of freedom for the error term, just like we got SSE, by subtracting off the degrees of freedom for treatment and blocks from the total degrees of freedom. All right, sum of squares for treatment now. That was given to us here. We worked that out to be 1.53. The sum of squares for blocks was 0.206 repeating. The sum of squares for error were calculated to be 0.540. Now the mean squares, remember how we do that? We divide the degrees of freedom into the value that's next to it, and that will give us the mean square over on the other side. So let's do that then. Let's go ahead and do 1.53 divided by degrees of freedom 3. And we get the answer 0.51. And if we do 0.206 repeating divided by 2, we get the answer 0.103. Of course, that makes sense since it's half of 0.206. And of course, that 3 is repeating as well. And of course, if we put this in there, we'll get the 0.9 value. So 0.540 divided by 6. And you see, of course, we get 0.09, which is the result when you do 6 into 0.54. Now, we don't have to fill in this quantity, and we don't have to fill in this quantity, right? Don't need that, of course. There's no space for that. We don't need to fill in that space. We also will not need to fill in this square or this square. So these can be left blank. We do need to come up with these f values here, though. And the way you get the f value here is you have to do for the treatment one. We've done this before. To get this value, this f statistic is going to be equal to MST over MSE. That's where this one comes from. Now, if you think about where this one will come from, this f statistic would come from MSB over MSE. The reason why you would calculate that statistic is if you wanted to test to see if the blocks had a significant effect on the variation in the sample. And if you do that, if you figure that out and determine that blocks do indeed have a significant effect, then you know that you had a good idea to separate out the data in blocks. If it has no effect, then maybe in the future studies you certainly would not need to separate the data if the block effect is marginal or unimportant. Okay, let's work out the f statistics then for these two things. In order to do that, we're simply going to do the ratios that I described here. So we're looking at MST over MSE. Here's MST. Here's MSE, the last one. So we're going to do 0.51 divided by 0.09. Okay, so 0.51 divided by 0.09. And when we do that, we get the answer 5.6 repeating for the f value. 5.6 repeating. And we do the same for blocks, but we do the value 0.103 or MSB divided by MSE. So we're going to have 0.103 repeating divided by 0.09. And when we do that, we get the answer 1.15. 1.15. Okay, so those are our two f statistic values. This f statistic value is reasonably big. We might be able to reject the null hypothesis here. And this value is kind of small. If we're going to run a hypothesis test, we have very similar HO and HA, except for this hypothesis test regarding blocks, we'd be testing to see if all the blocks are the same, or the means for the blocks are all the same, versus at least one differs significantly. Let's just run our test on what we're supposed to run it on in this problem, which is basically on the treatment. They asked us to determine if this was in fact true, this claim. So let's run this test on that. In order to do that, then we have to go ahead and draw a critical value, or rejection region, find the critical value and compare this f stat to our critical value. So let's do that next. Okay, so let's find our critical value. So we'll draw our curve as a visual aid here. Remember the f curve looks a little bit skewed on the right-hand side, right? Or heavily skewed on the right-hand side, and starts out at 0 here. We have the number line down here, and we're looking for this critical value. That would be right here below on the number line. That critical value will be an f value, f statistic value. In this problem, if you look back, it said that we have a 5% significance level, so we're going to use 0.05. And what we're looking for here is the degrees of freedom used for the test statistic for the numerator and the denominator, and we'll put them in that order. So the numerator, in other words, degrees of freedom for the treatment value is going to be 3. And that will be afterwards divided by here, this MSE value, and then had degrees of freedom of 6. So our numerator degrees of freedom for our fraction is 3, our denominator degrees of freedom is 6, and that's what we're going to go to the table and look up. Numerator degrees of freedom 3, denominator degrees of freedom 6, and alpha of 0.05. So we'll go to the 0.05 table, look up those degrees of freedom, and get our critical value. Let's go do that now and see what we come up with. Okay, so we're on the 0.05 table. We're looking at numerator degrees of freedom 3, denominator degrees of freedom 6, and we get the answer 4.76. Okay, so we found our critical value to be 4.7571. 4.7571. All right, so that's our critical value. Let's compare that against our test stat, F. And that test stat was 5.6 repeating. And basically 5.6 is clearly in the rejection region. So we're going to say that we reject HO and therefore support HA. And with those conclusions in mind, let's go back to our claim and ask ourselves, is our claim HO or HA? And the claim was HO. So we're going to be wording our answer like this. We're going to say the sample data allows us to reject the claim. So the sample data allows us to reject the claim. And of course, the claim is that all the means are equal, or the graphite coders all work the same, right? So we're rejecting that claim that they each have the same mean light box readings. All right, so that's it.